themselves without external guidance from an outside source. Molecule is just two atoms held together by a covalent bond, and a covalent bond is just a stable bond attracted and repulsive forces. How does it work? MSA uses a bottom-up approach as opposed to a top-down approach. A top-down approach would be you have a block of matter, you shape it, you cut it to form whatever you want to do with it, with the circuit board for example. Bottom-up is you use the chemical properties of the molecules, and these come together and self-organize into a structure. For example, us ourselves, our DNA, proteins, the lipid membrane, which is a barrier around the cells, all that comes together without any guidance from anything or anybody. For example, picture A, this is a building block of DNA, and these come together and form the picture on B, which is a DNA nanogrid. Early difficulties, this was around 1995. They had the sources on this website. They didn't know back then how these things came together, how the biological systems actually did this self-assembly of proteins. But they did know they were working on self-assembled monolayers, which is a type of structure of MSA, but it's not a general solution to MSA. These are some pictures they had on an article. The main one here would be D. So they have using molecular electronics, so they can use it to either deflect depending on the properties and the molecules used. They perform different. They have their own different properties. Now in 2006, what they're doing is they're using synthetic chemistry. So pretty much we're doing this, and what we do is we construct the building blocks, and then through weak intermolecular bonds or van der Waals bonds, they come together, they form a structure, and since these are weak bondings, we can actually correct it at any stage of production. So it's going to be a cost-effective way to produce these and correct it at any stage, nanowires, transistors, or sensors.
We got transistor here. Molecular cell assembly is used with transistors. Here we see A is a molecule used for self-assembly, and B is the semiconductor molecule. And here we see how it is. We have the source, the drain, and the gate. And here's the self-assembled dielectric layer. You want this to be as thin as possible. And here's just a semiconductor layer. And this is just another picture of like a organic transistor that uses the self-assembly monolayer, dielectric monolayer. We see that it's in between the gate and the semiconductor, and obviously we know how source, drain, and the gate transistor works. Organic transistors are used in plastic electronics. We have a whole presentation, so I'm not going into details. But we have organic material that's composed of self-assembled monolayers. And the current methods to produce plastic electronics is inkjet printing, lithographic etching. The ultimate goal with molecular cell assembly is to grab the molecules, put them in a beaker, and then just basically throw them like a plastic thing, and that's going to be your circuit, just by molecules combining themselves together. Yeah. Some of the organic materials are, some of the problems that the materials are not stable. They won't produce reliable contact, and with the exposed to air, a certain atmosphere, it changes its properties. Therefore, it's not very stable right now, but they're working on it. So in the future, you're just going to be able to throw chemicals in one beaker and mix them together, and you won't have your circuit.
That consists of an area that is has been developing over the past couple decades called DNA nanotechnology. But DNA nanotechnology is trying to use the properties of DNA to make logical functions happen. So you can make your gates out of DNA, but through transferring molecular transferring molecular elements of DNA. So it is estimated that a gram of DNA will contain about 10 to the 8 terabytes of information. And what people are trying to do is to be able to use that. So anyway, this triangle over here is an example of a self-assembled molecule that is the exclusive OR gate. That exclusive OR gate requires four DNA elements and two with the input and the output, and the inputs to self-assemble completely. Let's see. Which leads me to this circuit here. This circuit here is from a press release from Caltech of about a year old. At the time, it was the single largest synthetic circuit of its type ever made. Those what that is you have 4 inputs. It'll compute the square root of a 4-bit integer, and it'll output it. Let's see, but it rounds it down to the nearest whole number. This computation takes about an hour to do. 10 hours to do. So at the moment, it is not very. It's not going to replace semiconductors anytime soon, but they're thinking of using these for medical diagnostics, therapeutics, and things like cancer detection. On top of that, as recently as this year, they've been using DNA from salmon to store data, and you can probably look that up. And it's just pretty. Some stuff that's just really developing at the moment, just going pretty slow, but it's developing.
So overall, it's an expensive way to produce nanotransistors or any nanoscale device. So we're going to use our 2006 manufacturing since they come together. An article I found dated from last year was the processing time decreased from 36 hours to 1 minute for glass copolymers patterns using microwaves. So they took their polymers, put it into the microwave, and heated it up, and that caused a chemical reaction and decreased the processing time for a transistor. So we can exploit this hopefully in complex structures like computer chips. That's it.